As we all know, the development of network goes so fast that more and more people are starting to use wireless networks. In wireless networks, a packet loss can not only be caused by a real congestion, but also it can be caused by the noise in the radio channel. In this way, if we regard the packet loss as an indicator of a real congestion, it is not totally right. However, as for the most widely used TCP variant, which is called cubic, it does not have the mechanism to detect whether the packet loss is because of a random loss or a real congestion. And every time it encounters the packet loss, it will just directly deduct the congestion window by 30%. And as you can imagine, if the random loss rate is very high, it almost can't utilize the bandwidth. In this way, my final year project is to implement a new TCP variant, which is based on cubic, but I also add some new mechanisms that I get from other sources to improve its performance under wireless networks. Here comes to the methodology. First, I want to talk about the mechanisms that I have used. I mainly used 4 mechanisms in this algorithm. The first one is the cubic growth function. This one is inherited from the original cubic. Every time it deducts the congestion window because of a packet loss, it will not increase the congestion window linearly. Instead, it will use a cubic function to grow it. As you know, a cubic function grows much faster than a linear function. In this way, it can make my algorithm fully utilize the available bandwidth much faster. As for the second one is the high start mechanism that can tell us what is the time to exist the slow start phase. Cubic high start is an improved version of TCP cubic. In the original cubic, in the slow start phase, it will grow the congestion window exponentially. Since the exponential function grows so fast, at the time it exists the slow start phase, there will be a large number of packets loss and retransmission. To avoid this, high start has a mechanism to detect whether the congestion window is almost equal to the bandwidth and delay product, which is called BDP, to make the algorithm exist the slow start phase much more smoothly. The third one is the estimate available bandwidth mechanism, which is get from TCP Westwood. It will continuously monitor the rate of returning acknowledged packets to calculate the sample throughput. It will use the sample throughput together with the estimated bandwidth calculated last time as the inputs of a low-pass filter to calculate the estimated bandwidth. The low-pass filter will be passed twice to make the output to be more smoothly. However, there is a problem that since the sample throughput only counts for a small part of the low-pass filter, it will increase the estimated bandwidth will increase very slowly. As for the last one, it's the most important mechanism. It is the random loss detection mechanism. I get this from TCP Vino. It uses the difference between the actual throughput and the estimated throughput. Based on many experiments, it gets a constant value for the threshold. If the difference is larger than the threshold, it means that the packet loss is due to a real congestion. However, if the difference is smaller than the threshold, it means that the packet loss is just a random loss and we can ignore it. After knowing these mechanisms that I use, first I want to talk about what I did last semester in this algorithm, and then I'll talk about the things I added this semester. As you can see from the pseudocode, I changed the function which is called big TCP recalculate as a threshold. First, it will detect whether it is a random loss. If it is a random loss, it will reset the congestion window to be the estimated bandwidth and the original congestion window. So it will not detect congestion window. But if it is a real congestion, it will it will set the congestion window to be the maximum between the estimated bandwidth and the deduct by 30% value. Last semester, I implement all the algorithms in simulation, in which no matter how many experiments I have done, the results are the same. So I can't find the problem of my algorithm. In this semester, I re-implement it in Linux, and I test all my algorithms in the EmuLab, which can perform emulation. And every time the results are different, I found two problems. The first one is the cubic function continuation. As you know, I have reset the congestion window to be the value I want. However, it will affect the inputs of the cubic function. Every time it encounters the packet loss, it will stop the original epoch and start a new epoch, which means that the cubic function will be restarted. If I reset the congestion window, it will start from the middle point of the cubic function instead of from the lower point. So it will start from the lower growth point, and if the random loss rate is very high, it will always be in the flat point, so the growth will be very slow. In this way, I changed the algorithm and I reset it. Only if there is a real congestion, I will start a new epoch. Instead, I will just keep the cubic function grow. As you can see from these two figures, the left one is the one I implement originally, that it will grow very slow since the maximum value is the estimated bandwidth. However, as for the second one, it will use the cubic function to grow. And as for the second problem, it is the exist slow start phase problem. As you can see from these two figures, if I test for 10 cases, there's always one case or two cases that it exists the slow start phase very early. This is because that at that time it encountered a packet loss, because in the mechanism of slow start, if there is a packet loss, it will exist, no matter what kind of the packet loss is. So I've tried many different mechanisms, but I found I can use the high start existing point detection mechanism to implement this. So I add a flag only if the high start detect the congestion window is going to be equal to the BDP. It will set the flag to be 1, and it will allow the mechanism to exist the slow start phase. Otherwise, if the packet loss is just a random loss, it would continuously to grow the slow start phase. Here comes the results and conclusions. To test my algorithms, to test the cubic plus, I implement all the things in EmuLab. The topology is shown below. There is a left side. The left side is the client, and the right side is the server. And in the server side, I have installed Apache, and I have downloaded several packets of fixed size. And as for the bridge, I use the DummyNet, which I can set the network conditions. In in the experiments, I have tested the 3G and 4G cases, and every time I set the in every experiment, I set the TCP variant in the right server, and in the left side, I use wget to get the packets of fixed size from the right server, and then I record the flow completion time of each time, then I get the results. As you can see, these figures are the FCTs that I get. This figure shows the average FCTs of 10 cases, and in the left side, the random loss rate is 1%, and the right side, the random loss rate is 0.01%. As you can see from these tables, Cubic Plus can really make some difference in wireless networks. How the higher the random loss rate, the better the performance of Cubic Plus. I also tested the fairness of Cubic Plus, and I set the network bandwidth to be 30 megabit per second, and the random loss rate to be 0.1%. As you can see from these two figures, no matter when the other flow starts, after the first one, they will finally fair share the bandwidth. In this way, Cubic Plus can really is really fair to itself. As for the future direction, because last semester I used simulation, and this semester I use emulation, which is much like the real network, but it is not the real network. In the emulation, I still need to set the network conditions instead of make the network condition to be random. So I guess in the future I really need to implement the algorithm in real network conditions to see whether it can perform well in mixed environment, which means there are wild and wireless parts. Here comes the references, and only some part of the references because the space is limited. And as for the final, I need to show my great appreciation to Professor Jack Lee and the TA Guo Lingfeng. Thanks.